Hey, now let us discuss Schrodinger's wave equation. So this is a fundamental equation of quantum mechanics. So now let us understand what they study in quantum mechanics actually. See, quantum mechanics is such a branch of science where we study the properties of quantum particles. Okay, so it is a branch of science, so very important branch of science where we study about quantum states. Okay, so quantum states of the very microscopic particles, quantum states of quantum particles. So what do you mean by quantum particles here? Quantum particles are those particles which are microscopic in nature. That means the very small particles like electrons, protons and etc. Okay, so now what actually we mean by quantum states? So the de Broglie and everybody else, Einstein and everybody else have told us every matter, okay, so the previous experiments prove that every matter has got the dual nature. Okay, specifically the dual nature is more prominent, this particular dual nature is more prominent in these microscopic particles like electrons. Okay, so according to all of these scientists, the electron is more like a wave. Okay, so electron moves like a wave, it moves like a wave. Okay, it behaves like a wave, now. Okay, and electron, in fact electron itself is a kind of a standing wave, right? So now when we consider electron itself as a wave, then how does it move around the nucleus? So we know in an atom you have nucleus at the center, and so far what we have studied according to Bohr and other scientists is, so you have the trajectories, so you have something called orbits around the nucleus and the electrons keep on moving in these orbits. This is what we studied about an atom. Okay, so usually when we explain the concepts regarding atoms also, we put this kind of picture to show the atom. Okay, but practically speaking, in reality, atom will not move in this specific trajectories. Atom is not moving in this specific orbits. Okay, instead, suppose if this is a nucleus, okay, right? So a particular atom can move in a three-dimensional space in the form of a wave. Okay, so some moment electron can be here, some moment electron can be here, some moment electron can be here, some moment it can be here, it can be here, it can be here. There is a specific space. Okay, so there is a specific three-dimensional space where you have maximum probability of finding an electron. Okay, so where do you find an electron? You cannot exactly locate at this point electron is there. You cannot exactly locate at this point electron is there. But you can say the probability. You can actually say, this is the area. This is the area altogether around the nucleus that my electron can be there. Okay, so now there is no something called orbits. The concept of orbits is completely wrong. Okay, so now what you have is the concept of orbitals you have. So what is a orbital here? The probability of finding an electron at a particular three-dimensional space. Okay, so this is the available space around the nucleus where I have a maximum probability of finding a electron. Okay, so that is what we call orbital here. So now there is no concept of orbits anymore, it is the orbitals, right? So electrons, if the electron, say this is a nucleus, if the electron is moving like this around the nucleus, say electron can be here, 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 a particular electron is moving in this fashion, it's a wave and it is moving in this fashion, right? So if I ask you what is the position of that particular electron, say electron can be here, it 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 can be here, anywhere, but it is moving in a particular region, three-dimensional space around the nucleus. Okay, now what I say is this entire region is what we mean by orbitals. So actually orbitals have got different shapes and different sizes. So wherever to whatever extent it want, it can move. I mean the electron. Okay, so it is the three-dimensional space where you have maximum probability of finding an electron. So I repeat once again, three-dimensional space. Okay, so where you have maximum probability, so very important, probability of finding an electron, okay, so that is what we call orbitals. Okay, so there are so many three-dimensional spaces available for different electrons. Say one electron can move in this fashion, the other electron, you don't have only one electron in the atom, you have so many electrons. Say some of the electron can move like this in a radial fashion, in a circular fashion. Now what do you say is this much space is the available space for finding an electron. Okay, so where exactly you find here or here or here or here, don't know, but I have a probability, I have a maximum chance of finding in this much area. So that area around the nucleus where you have maximum chances of relocating an electron is what we mean by orbital. So now how do we know about these orbitals? How do we know what atom has how many orbitals, so which electron is moving in which orbitals? So this information about an electron, say not only the position of electron, here I have discussed the location of electron, the position of electron, but the electron can have energy, yes, the electron can have different measurable properties like speed, momentum, etc. So how do you find the entire information about an electron? Okay, so the entire information of an electron is hidden in the factor called wave function. So electron is a wave now, electron is a standing wave. Okay, so now if you can find out the amplitude, okay, so this distance is called amplitude, isn't it? So this amplitude is technically called as psi. Okay, so what scientists say is if you know the value of psi, you know that psi itself contains so much of information about an electron. Okay, so let me write this. So this psi, in fact, it can be called as wave function. So this wave function, which is denoted as psi, okay, this wave function has got complete information. It has got complete information. What do you mean by complete information here? Complete information means it helps you to find out where exactly electron is there. That means location, energy, okay, and as well as momentum, that is speed. So this is what we mean by complete information. Okay, so psi has got complete information about an electron, Okay, yes, so it is a mathematical function. So this psi is there, no? So another point, very basic point, psi is mathematical function. So it's a hypothetical mathematical, I mean it's an imaginary function actually. It's an imaginary function, but technically speaking psi is nothing but amplitude of a wave. They considered electron as a wave, and any wave will have an amplitude, and physically the psi is nothing but the amplitude of a wave. Okay, but practically speaking it will give you so much information about an electron. It will give you where exactly electron is there, what is the energy, what is the momentum, everything it can able to tell about an atom in fact, or about an electron in fact. Okay, so psi is mathematical tool which has every information about an electron. Okay, mathematical tool, and it can be solved. It is solved. Yes, the values of psi will tell you location, energy and momentum, but you have to solve the psi, right? When it is a mathematical tool, you have to solve it. You should get values by solving it, isn't it? So it is solved through or solved with the help of Schrodinger's equation. Solved with the help of Schrodinger's equation. So very interesting, right? So that is the importance of Schrodinger's equation here. Okay, so see here, I told you the quantum mechanics is a branch of science where we study about the quantum particles. Quantum particles means electron, proton, etc. Okay, so here there comes Schrodinger equation, which is a foundation for everything. So what does the Schrodinger equation has? Schrodinger equation has something called the wave function psi. So why psi is important? Because it contains all the information relating to the electron. Now it is a mathematical tool, you have to solve it. To solve it, you should have an equation, and that equation itself is called as a Schrodinger equation, which is the equation which I am going to write now. Schrodinger's equation can be written in two basic formats. One is a time dependent equation, the other one is time independent equation. Okay, so now for you all I am giving Schrodinger's time independent equation. Okay, so it's very simple actually. Del square psi del x square plus del square psi del y square. Okay, del square psi plus del z square plus 8 pi square m by h square. Okay, E minus V psi is equal to 0. Here del square by del x square, this is the second degree of differentiation, isn't it? So let me tell you what are x, y and z here. X, y and z represent space coordinate. Okay, they represent space coordinates. That means in simple terms they represent three-dimensional space. Yes, electron and etc. they are there in three-dimensional space only around the atom. Okay, so x, y, z represent that three-dimensional space. Fine. And now yes, psi, about psi already I told you, psi is called as a wave function. Psi is called as a wave function. Here it is independent of time. Sometime psi can also be represented as psi x comma t, which means that time dependent wave function. That means psi keeps on varies according to time. Okay, so whenever we write in some books, psi can also be mentioned this way. It means psi is a function of one of the coordinate as well as time. Okay, that is what we mean by psi xt. You can either write simply psi or you can write psi xt also. Okay, so both represent the wave function, right? And then okay, So here let me write psi can also be written as x comma t, which is a function of one of the coordinate, x coordinate, or x represents the position also sometimes, and time is also depending on time. Okay, so when psi depends on a time, we write it this way. When psi is independent of time, you can simply write it like this. Okay, yes. So now you know pi is a constant, and here m is nothing but mass of an electron. Suppose if you want to find out all information about a particular electron, it is mass of electron. Okay, and h is a Planck's constant. So this is a Planck's constant, right? And coming to E is nothing but total energy of a system, and V is nothing but potential energy. So potential energy of a system. Okay, so this is the Schrodinger equation, guys, right? So when you solve this equation, right, first step is to write a Schrodinger's equation for a particular atom. So see, I am going to tell you how do you get all the information about the psi. Okay, so what is the process of finding an information? So what is the process of finding everything about a particular electron? So first step is you have to write Schrodinger's. You have to write Schrodinger equation for an atom. Okay, so for hydrogen atom we write differently, for oxygen atom different, for helium atom different, like this. First you have to write a Schrodinger's equation. So after that you have to solve this equation. So solving this equation is quite complex, and you will learn it in the next classes actually. Okay, so solve this equation and get values for psi. Okay, so you will actually get values, certain values that you will get for psi. Okay, but those values are not simple. So though you don't get values in some real numbers like 5 or 2. When you solve something you get some simple values, right? But when you solve psi you will not get simple values. So you have to take some values which are meaningful. You have to discard the values which are not meaningful. Okay, right? You should know which values to be considered and which values to be not considered. This is very important. So now let us talk only about the psi. Okay, what is its importance? Okay, what values of psi have to be considered? So all the properties and nature of psi we will discuss. Okay, so far I have given you the basic level of understanding on Schrodinger's equation and the function called wave function or psi. Now we will discuss what exactly is this wave function. So what exactly is this wave function, that is psi, and its significance. Okay, significance in the sense its importance. Okay, so wave function psi. So what is its important? Wave function is the function. It physically represent, it actually physically represents what? Physically represents amplitude of a wave. Amplitude of wave, right? So they said electron is a wave, and we know this distance. Yes, so this distance is called as amplitude. So it physically represents amplitude of a wave, but it gives every information, right? But it gives every information of an electron. Okay, every information means what? It can talk about the location of an electron, that is where exactly electron is there. It can talk about the energy, it can talk about the momentum and various other things that is relating to electron. Okay, so now usually let us discuss the nature of psi actually. Okay, so what are the different points that you need to keep in your mind to observe the values of psi? So what is the nature of wave function or psi? Okay, so the first and foremost, let me show them in the next page. Nature of psi. Okay, so usually the psi values are complex. Okay, psi values are complex. So you don't get simple values of psi. Okay, so you will get very complex value of psi. You know, 5 plus 4i. So what do you call? This is a complex number, right? It's a very different number. It's not a usual number. So psi values are always complex. Okay, and psi values should be finite. Okay, psi values should be finite, or psi should be finite. Let me write this way. Psi should be finite. That means you should not get infinite values of psi. You should get some finite value of psi. Okay, and psi values should be continuous, or just psi is continuous. Psi represents for continuous standing wave actually. Okay, yes, and also function must be function in the sense psi only. Okay, so function must be single valued. You should get single values for different measurable properties. Okay, so it should be single valued, and also function should be integrable. Okay, so function should be integrable. Function should be double integrable or double differentiable. Like you have to the values of psi can be you should able to do second degree derivations. Okay, with the values you must able to do not the first degree differentiation alone, second degree differentiation also you must able to do. That means you should able to apply second degree differentiation to the psi values. Second degree integration, second degree differentiation, mathematical tools can be applicable for psi. Okay, right? So these are certain conditions for the better psi values. So if you observe these conditions for any psi values that you get out from Schrodinger's equation, then those psi values are acceptable psi values. Okay, so if you observe these conditions, okay, so if you observe these conditions for a particular psi, okay, for a particular wave function, then they are called acceptable. Then they are called acceptable psi values. Okay, so acceptable values we say. So that's very important. That means all values of psi will not give significance or will tell everything about an electron. Only if the values satisfy these conditions, they are called as acceptable psi values, and they will help you out to give information about location or position, various other things like energy, momentum, and etc. Okay, yeah. So having studied that much, now let us also understand about what exactly we mean by psi square. Psi square is usually called as probability density. Probability density. Okay, right? Say imagine you got a psi value of around, actually when you square the existing psi value, you will get probability density, which means you will get to know the location of electron. You will get to know the location of electron, guys. Okay, so by squaring a psi value, you will get to know the location of electron. Okay, so this probability density itself is called as orbital. So the starting I told you, right? So the starting I told you, the electron, since it has got a wave nature, it doesn't move in a circular trajectories. It would move in the form of a wave, and it will move in three-dimensional space, and you cannot find exactly where is the electron, but you can find the probability. You can find the entire region where the electron is most of the time spending its life. Okay, so that is what probability. This area is called probability density, or in other words we called it as orbitals. Okay, so here this psi square is there. No, the psi square, yes, let me go to that page. This psi square directly represents orbitals. That means the psi square will give you the probability density, that means maximum times where exactly the electron can spend its life. That idea is given by the values of psi square. Okay, actually psi values do not have any meaning. Psi square, when the values are squared, then the values can have meaning, and they will tell about different aspects of the electron, guys. So this is all about the wave function and its significance. Now let us discuss about normal wave function and orthogonal wave function. Normal wave function and orthogonal wave function. Okay, so they are very simple, guys. Normal wave function can also be called as normalized wave function here. Normalized wave function. Okay, normalized psi. Okay, so first let us understand what is a normal wave function. So the wave function to be valid, okay, so remember it carefully. The wave function values, okay, values to be valid, okay. So I told you all the values of wave function does not give you all the information. Only few values of wave function has to be considered. So if a wave function values has to be valid, then there are certain requirements. Okay, so then there are certain requirements. Okay, say just like for example, if you want to get admission to 10th standard, what is the requirement? You should able to qualify 9th standard, right? You should able to pass 9th standard. Just like that, for any class to enter next, what is the requirement? The requirement is you need to qualify the previous class. Just like that, if the values of wave function to be valid, then there is a requirement. So what is the requirement is, it's very simple. Say for example, electron is moving like a wave. Electron can be present anywhere from minus infinity to plus infinity. Imagine this is the total area. From here to here, electron can be there anywhere. Electron can be here. This small space is called as dx. So electron can be present here. This is another dx space. Electron can be present here, another dx. Okay, so now when I integrate from minus infinity to plus infinity, from this to this, so I'll integrate all of these dx's, right? So when I solve psi square, okay, so when I integrate psi square, I told you, no, psi square is what that represents the probability density, or it represents the region around nucleus where you have maximum chance of finding an electron. So when you integrate psi square with respect to dx, you should get the value 1. Okay, this is the condition, guys. So it is those psi values which are valid when its square values when you integrate from minus infinity to plus infinity, you should get the value 1. So such a wave function, for whichever the wave function value you are getting the value 1, then those wave function values are the correct values. Because what does the psi square represent? Psi square represent the probability density, right? Probability can be 100%. Say whenever you say about probability, you cannot have negative value. Probability should be 100% when you say about probability, isn't it? Right? So the chances of finding an electron must be 100% with respect to a particular location. It should not be like 40% chance is there, 50% chance is there, minus 10% chance is there. Chances will not have a negative value. Chances means 100%, right? So that is what that 1 represent. Okay, so what does this 1 represent? What does this 1 represent? Okay, so this I'll write that once again. Integration from minus infinity to plus infinity, when you integrate psi square values with respect to dx, you will get the value 1. So this 1 represents, there is 100% probability, there is 100% probability of finding an electron. Probabilities cannot be negative. Okay, so probabilities cannot be negative. Okay, so those wave functions, when you do this integration, you get 1 in the sense, if you get 1 in the sense for those wave function, when you integrate, then those wave functions are valid. Okay, so this is a requirement. So whenever you get psi square values, you have to do this small integration for that psi square values. If you are getting 1, then those psi square values are the values which are correctly talking about what? They are correctly talking about orbitals. Okay, so they correctly talk about orbitals. It is those psi square values. Okay, so those psi square values, okay, so which satisfies this condition, okay, this condition, then those psi square values are giving you correct values of orbitals. Okay, so that is, such wave function values are called the wave function values. When you integrate with respect to dx, if you are getting a value 1, then those wave functions are called as normal wave functions or normalized wave functions. Okay, so that is all about normalized wave function. So now orthogonal wave functions. So what do you mean by wave functions are orthogonal? Okay, in case if any wave function is not normalized, by multiplying with certain constant, they obey that normalization. Say we sometimes purposefully make wave functions normalized by multiplying with some constants. Okay, yes, you have to use the normalized wave functions only for many of the calculations. So that's why, practically speaking, even if a wave function is not normalized, if it is not satisfying normalization, we will multiply that with a constant and we will make it to satisfy to a normalized condition. Okay, for doing various other calculation. Okay, yeah. So now orthogonal wave function. So imagine you have two types of wave function. Okay, so suppose consider psi1 and psi2 are two wave functions. And psi1 star and psi2 stars are the complex conjugates of psi1 and psi2. So what do you mean by complex conjugate? Suppose if you have a number 2 plus 3i. Okay, what is its complex conjugate? 2 minus 3i is a complex conjugate. Okay, like that. So if this is a particular number, its conjugate is 2 minus 3i. So 5 plus 4i, what is its complex conjugate? 5 minus 4i will become a complex conjugate. Okay, right? So if psi1 and psi2 are two wave functions and psi1 star is a complex conjugate of psi1, psi2 star is a complex conjugate of psi2, because these psi values are all complex numbers. Okay, so that's why I have taken those examples and told you, right? Okay, so now when you integrate from minus infinity to plus infinity, when you integrate psi1 star, okay, with and psi2 with respect to dx, you should get 0. Okay, see, you're taking a product of, you're taking the multiplication of complex conjugate of one wave function and the normal wave function. Okay, so the original wave function of the other one, right? So see here, psi1 star is a complex conjugate of psi1, whereas psi2 is a normal wave function value. So when you integrate this, when you do this calculation, I mean one of the wave function should be in conjugate form, the other one is in a normal way. So when you do this calculation, you must get 0. Only then those psi functions are valid and it actually represent. So the real meaning behind this is it actually tells that two orbitals are not overlapping. Two orbitals are not overlapping. Or if I have to go much more deeper, you know, single electron, a particular electron, single electron cannot be present in two different orbitals. So this is the meaning, guys. Okay, so this mathematical expression, this mathematical way of writing has got this meaning. Okay, right? So if a wave function value satisfies this condition, then those wave function values are actually valid. It means that a single electron cannot have cannot be moving in two different orbitals. Okay, so the electrons are independent, they move in a particular orbitals, they won't move in two orbitals or three orbitals at a time. Okay, right? So that is what the meaning of orthogonal wave function. So hope you understood about normal wave function and the meaning of orthogonal wave function.